Hello students, this is our second lecture. In first lecture, we have studied introduction to MOSFET and DC analysis. What is the syllabus in this unit and the design challenges for Mos transistors or integrated circuit or scaling industry, and what is the difference between bipolar junction transistor and Mos transistors. Today we are going to study the construction of MOSFET, biasing of MOSFET and its ideal voltage current characteristic or VI characteristic of MOSFET in detail. Let us begin with construction of MOSFET. So, already I have drawn the construction here. So, MOSFET. So, this is the construction of N channel MOSFET. N channel MOSFET, simply it is called Nmos device. See what is in the construction. So, this body, this complete body is called P substrate. So, this is of P type semiconductor material. So, it is P type substrate and one terminal is taken from this and it is labeled as SS substrate, or simply it is called body. It plays an important role in the characteristic of the device. Later we are going to study the body effect, what is the effect of this body on the conduction or working of the device. So, this region is lightly doped. We should write this because we have to understand the concept working of flow of current in the device. Therefore, if we label this, we can understand from where the charge carriers are coming. So, this device is lightly doped. Now, what is the meaning of this? As it is lightly doped and it is P type semiconductor, it means the majority charge carriers are holes there and electrons are minority charge carriers or current carriers in the structure. This whole structure is P type substrate. Now, see N plus semiconductor is deposited here, 2 N plus regions. This one region constitute source and the second region constitute drain. So, let us label this. So, this portion, this complete portion is source and this complete portion from this to this. So, it is the drain region. I have not connected the external leads yet. I want to explain this portion, how it is built. Now, see this, below this exactly about the substrate and this portion, first I will tell about this. So, this portion is polysilicon material and it is simply a metal. Okay. Do not call polysilicon, heavily doped polysilicon, just remember it is a metal. So, this metal and the substrate is separated by a thin oxide layer. So, this one is, it is the oxide layer, oxide, and it is silicon dioxide. A thin layer separates the P substrate and this metal, and from this metal a terminal is taken out, and this is the gate. The most important terminal in the Mos transistor is the gate. And now see, this N plus region is directly connected with external lead using metal. See this. So, it is the metal and one terminal is taken from this and this is the source terminal. Again, N plus region is directly connected using metal to external lead and this terminal is the drain terminal. We have gate, source and drain. We have 3 terminals from the device. Actually, there is fourth one is also there. This one is, this is the substrate or body terminal. Okay. So, this is also important terminal we have to consider while making the circuit using Mos transistor. Now, this is N plus heavily doped and this is lightly doped. One thing, what is the most important region here? we have to remember that the area below this oxide layer, here the channel is going to form. Okay. So, how the channel is going to form in NMOS we are going to study, but before that, what are the dimensions of the device? The device dimensions are in nanometers and it is extremely small. It is manufactured under microscope and here it is exaggerated to understand the working of the device. So, huge structure is shown here. What is the thickness of the oxide layer? Tox is thickness of oxide layer and it is around approximately 15 angstrom. So, what is angstrom? So, it is angstrom is unit of measuring length and 1 angstrom is equal to 10 raised to minus 10 meter. It is very small unit, or we can measure a small quantities using angstrom. Now, length of the channel. So, this where is the length? So, here and where is the width of the channel? So, this portion. So, this is the L effective. So, it is the length of the channel and where is the width? So, this one is the width of the channel. See, channel is not here, channel is going to form below this oxide layer and it is having width like this and the length of the channel is like this. Okay. Where we are going to study the channel length modulation, it means that it is going to change the length of this channel here and width is under this oxide layer from this point to this point. Now, what is the length of the channel? So, L is the length of the channel and it is around approximately around less than 10 nanometer. Day by day this size is shrinking, it is becoming smaller and smaller. At present we do not know what is going on in the industry. So, we have written approximate 10 nanometer, less than 10 nanometer and W is the width of the channel, and it is approximately less than 6 nanometer. So, these are the dimensions of MOS structure and exactly opposite to this, when we take N type substrate and P plus and P plus, it is the construction of the PMOS or P channel enhancement device. Let us apply the voltage across the device terminals. It is called the biasing of the MOSFET. We are going to understand the working of N channel A MOSFET, or this device simply it is called Nmos, and the symbol of the Nmos is this one. Drain, source and gate. An arrow is shown on the source. We are going to use this symbol when we will be studying the biasing circuits of this Nmos. The device is biased by using different DC voltage sources. Voltage source 1 connected to drain and voltage source 2nd connected to gate, and source is grounded. First of all, why we need DC sources? We are studying the DC condition, DC analysis of the MOS transistor, and as it is a semiconductor device, we have substrate here. So, it is P type substrate. So, it is the body of the transistor, and we have to make the movement of electrons or the holes in PMOS we need DC voltage sources and we have to apply the proper voltages to make the movement of the electrons and holes in the device, semiconductor device. Source is grounded, gate is provided with positive voltage and drain is provided with positive voltage, and all the voltages are with respect to source. Here is the oxide layer and it is the metal to which we have connected gate, and metal directly connects the source and the drain here. So, this one is the metal. There is no oxide layer below this, only oxide layer is present here. So, this makes the Mos device. So, this device is the Mos device. So, Mos transistor has 3 layers. First layer is of metal. So, this one is metal, and second is oxide. So, it is somewhat larger, I will make it small, and this portion is the semiconductor. Say this. So, this is the substrate. So, it is S, O and it is M, and here we have positive voltage and here it is connected to ground. So, substrate is always connected to ground. Why it is connected to ground? I will tell you. See, so this resembles a capacitor. Okay. So, between two conducting plates, one dielectric material. So, oxide, silicon dioxide is used and it is a dielectric material. It has permittivity and these are very thin layers. Metal is also thin. Oxide layer, just like a line of water. So, thickness is measured in angstrom, and semiconductor, okay, it is the substrate material having some conductivity. As it is slightly doped, it has holes and electrons. Remember these points so that we can understand how the current flows in the Mos transistor. This Mos transistor works as the voltage controlled current source. That we have to understand how a Mos transistor or N channel MOSFET or Nmos can be used as a voltage controlled current source. That is our objective. We have to understand the working of the device. There can be different cases. Let us take case 1, when VGS is equal to 0 and VDS is greater than 0 volt, or we can say VDS is positive, it has some value, say 0.2, 0.3 like this. Now, in this case, what will be the current in the device? What will be the current and what is the direction of current? Now, see, as it is substrate, so it is P type semiconductor here, it is P type semiconductor here, it is P type semiconductor here. So, there is a formation of junction here. So, this region is having junction. What is the junction here? So, here we have substrate or drain, substrate junction. See, there is a depletion region between this P and N plus. Here also we have junction and it is between source and substrate. So, this junction is source substrate junction. See this, we have to reverse bias these junctions. Therefore, because of this, the substrate is always connected to ground in case of Nmos or N channel MOSFET. Remember this. In case of P channel MOSFET, the substrate is connected to higher potential, highest potential in the circuit, that is positive. Okay. Now, see, what is the current in this case? So, current in the device, it is around leakage current. So, leakage current is present here, leakage current present in the device. What is the amount of leakage current? It is very small, it is less than nanoamperes. We can say negligible leakage current is present in the device from drain to source. Okay. Second case, case 2, when VGS is positive or VGS is greater than or equal to VTN. So, it is VTN and VDS is greater than 0.2 volt or around 0.2 volt. VDS is greater than 0, let us say it is around 0.2 volt or greater than 0.2 volt, but it is of small amount, okay, because larger VDS has a different effect on the device current and smaller VDS has a different effect on the device current. Now, we are going to define VTN here. Now, see, first of all, see the effect of the voltage, gate voltage, then we will define the threshold voltage VTN. Now, see, here it is the positive voltage on gate. Now, see metal and it is oxide and here it is the p-type substrate. It is having electrons as a minority current carriers. So, what happens due to the inversion, due to the capacity effect, when positive is connected to one side of capacitor, automatically negative charge accumulate on the other plate. This is the capacitive effect. Now, see due to this what happens, electric field is produced here across this plate and negative charge, that is electrons accumulate below this oxide layer. From where these electrons come? So, this p-type substrate is lightly doped, it has electrons as a minority current carriers and these accumulate below this, okay. Now, when the current will flow, it is the when enough amount of inversion takes place below the oxide layer, at that time this electrons will flow from source to drain through this region, okay. And when it will happen? When we apply VGS positive enough, okay. So, that voltage is called as a threshold voltage, okay. When VGS is positive enough to form inversion layer below oxide between source and drain, okay. That voltage will cause channel induction. That voltage will cause channel induction between source and drain. Say this, it is the amount of gate voltage, positive gate voltage, which will cause inversion layer below oxide layer and enough charge carrier concentration is present below oxide layer and it is called as the induction of the channel. The channel is induced in Nmos device, okay. What type of channel it is? As electrons are accumulated here, are inverted, this region was p type, now it is completely n type and therefore, this region is called as inversion layer and this portion is nothing but our channel. So, it is the formation of n channel. So, it is said that n channel is induced, okay. The channel was not present between source and drain below oxide layer, the area has more resistance. Now, because of gate voltage, the channel is induced and because of this thing, this is called as MOSFET. E stands for enhancement. The gate voltage enhances the induction of the channel between source and drain. Now, here the role of VDS starts. So, it is positive here. Now, electrons from source get a channel to drain towards this terminal because it is at positive potential. Electrons are attracted towards this and they start moving through this channel and current flows opposite to this direction. The current starts flowing from this positive terminal, drain through this channel and through this source, and this is at ground. So, current flows from drain to source. The same thing is shown in the symbol also. Now, see here, this symbol shows the Nmos device. See, it is drain, source is at ground and it is gate voltage. So, we have applied VGS to gate voltage. So, it is positive voltage, and drain is at positive potential. See, it is positive potential VDS and it is VGS, and the current flow from drain to source. So, it is the drain and it goes to the ground source. Now, see, now same circuit can be shown as VCCS. Now, see, we can write this as a gate terminal, as a controlling terminal, and this symbol of MOSFET source and it is drain. So, it is, let us say it is. So, this operation tells that this device MOS transistor works as a voltage controlled current source. Now, say VGS is input. So, we can show this symbolically as, say this. So, it is the gate terminal, drain and source. Now, VGS is what? VGS is input quantity, and what is the quantity to be controlled here? It is the ID. So, ID is what? So, it is the output current, and VGS is what? Input voltage. Therefore, we can say that, so this works as voltage controlled current source. MOSFET is a voltage controlled device and it works as VCCS, voltage controlled current source, because it is the gate voltage which controls the output drain current.